Welcome to this course on transition metal organometallic chemistry from principles to applications. In our previous lecture, we were discussing about sigma alkyl complexes and their preparations. These complexes are an important part of organometallic chemistry, as they are intermediates for many catalytic processes. Hence, it is of importance that these complexes be synthesized so that they can be used for various application purposes. In the last class, as far as the synthesis of sigma complexes are concerned, we have discussed 4 preparative methods for making them. These involved the very common metathesis method, which included reactions of metal halide with organoalkyl compounds. The second method that we discussed was of an insertion reaction, an insertion reaction of an alkyl into metal sigma hydride complexes. The third one was another insertion reaction of carbene into metal sigma hydride complexes, and the last one that we discussed was metallate alkylation reaction, in which low valent transition metal organometallic compounds were reduced to form electron rich metallate anions, which were then reacted with alkyl halides. So, that gave us the scope of synthesis of these sigma alkyl complexes. There are few methods remaining which were not discussed in the last class and which we would be discussing in this lecture. Now, in continuation from the metallate alkylation reaction, there is the variant which is called a metallate acylation reaction. This method is the 5th method that we are discussing on transition metal sigma alkyl complexes. This is called metallate acylation reaction. And involves a reaction between a carbonylate anion and an acyl halide. This reaction is very similar to the last reaction that was discussed in the previous lecture, where it was called metallate alkylation reaction, and in this case it is called metallate acylation reaction, and the reaction is between a carbonylate anion and a acyl halide. I will illustrate this with this following iron metallate complex. Reacting with CH3COCl, giving minus chloride, giving this FeCO methyl moiety iron cyclopentadienyl dicarbonyl, which in presence of light eliminates the CO to form the iron methyl complex. An important characteristics of metal acyl bond is that the metal acyl complexes prefer to eliminate CO in presence of light or heat. Heating or light irradiation. So, this method was very similar to the previously discussed metallate alkylation reaction. Another very important method for preparing metal sigma alkyl complexes is the oxidative addition method. Now, oxidative addition is a very important reaction that is encountered frequently in the realm of organometallic chemistry in various catalytic cycles as well as in various synthetic reactions. A hallmark of this reaction is that the oxidation state as well as the coordination number of the metal increases by 2. So, as the name suggests that it is a addition of atoms onto the metal center. Let me illustrate it by this simple iridium complex. Which reacts with methyl chloride. Now, for something a metal complex to undergo oxidative addition in which the oxidation state as well as the coordination number increases by 2, the criteria for such addition is that the complex should be electronically as well as coordinatively unsaturated. Unsaturated. So, this iridium complex satisfies both because it has a coordination number of 4, that means it can still end up being an octahedral complex having coordination number 6. So, as far as the coordinative unsaturated concerned, as mentioned that this square planar complex is coordinatively unsaturated. As far as the electronic saturation is concerned, this complex is electronically unsaturated too, as it has 16 valence electron. So, it is also electronically unsaturated. So, this complex, which is both electronically and coordinatively unsaturated, reacts with methyl iodide to give this electronically and coordinatively saturated iridium complex, octahedral complex, having the methyl added to it. Now, the thing to note that this methyl chloride has added in a trans fashion with the methyl chloride has added in a trans fashion with the methyl and the chlorine occupied trans position, trans to each other. So, this kind of oxidative addition is often referred to as trans oxidative addition. This trans compound, upon further heating, organizes back to the cis compound as shown over here. So, both the cis as well as the trans compound are electronically and coordinatively saturated. As their coordination number is 6 and their valence electron are 18. So, what has been found that this method of oxidative addition require the metal complex undergoing the oxidative addition to be both electrochemically as well as coordinatively unsaturated, and which upon undergoing oxidative addition would show that the central metal atom has undergone an increase in the oxidation state by +2 as well as the coordination number by +2. Another example of oxidative addition is been shown now. Unlike the past reaction where oxidative addition happened in a trans fashion, a cis oxidative addition reaction is shown below. In this platinum 0 complex, methyl iodide undergoes oxidative addition. Here also the complex is both electronically as well as coordinatively unsaturated. Its coordination number being occupied by eta 2 alkyl 2 phosphine, and it electronically it has 16 valence electron. It undergoes oxidative addition to give this cis complex. where the methyl and the iodide are in cis disposition to each other, and this is called cis oxidative addition. Now, this TBP complex trigonal bipyramidate, which is a 18 valence electron compound, loses this ethylene to give another 16 valence electron square planar platinum complex having cis disposition between the methyl and the iodide moieties, and it is also a 16 valence electron complex. So, oxidative addition requires electron rich metal center. Now, if we look at various examples of oxidative addition, it would seem that the complex should have electronic unsaturation, that is, its total valence electron should be lower than 18 valence electron, at least by 2 valence electron unit. Now, that would imply that 18 valence electron might not undergo oxidative addition at all, but this is not true. Oxidative addition may also happen in a 18 valence electron basic metal complex. The metal complex electronically saturated in terms of having 18 valence electron, but should also be electron rich and basic for it to undergo oxidative addition reaction. For example, for the cobalt compound shown here, cobalt Cp carbonyl PpH3, which is a 18 valence electron compound, undergoes oxidative addition with methyl iodide, giving the compound Cp cobalt methyl PpH3 carbonyl that show a very characteristic reaction for such type of compound called migratory insertion of CO methyl into the cobalt CO bond, giving cobalt acyl compound as shown below. Now, if one were to look at the oxidation at the metal center, then one would notice that over here cobalt was in +1 oxidation state, over here cobalt is in +3 oxidation state, and over here the cobalt is in again +3 oxidation state. So, this is expected for a oxidative addition reaction that the oxidation state increase by 2. Apart from the oxidative addition reaction, another important reaction is this nucleophilic addition reaction. Nucleophilic addition reaction is very common to certain very specific substrates and mainly involved reaction between activated metal bound olefin with a nucleophile. For example, for this half sandwich CP compound of nickel undergoes nucleophilic attack in presence of methoxide anion to give the following nickel complex. As is shown here. What happens over here is that the methoxide nucleophile attacks on this activated olefin. The next reaction that we are going to talk about is nucleophilic addition reaction. This reaction is a reaction between activated metal bound olefin with a nucleophile. For example, in this cationic nickel Cp star diolefin complex, the olefin being bound to nickel is activated. In the sense, the electron density on the olefinic pi cloud gets transferred over to the metal. As a result, the olefin become activated and susceptible to a nucleophilic attack. So, a methoxynucleophile can attack a activated olefin, giving rise to a complex like this, and this talks about the Umpolong nature of olefin. So, Umpolong reactivity is a very important concept, which means reversal of polarity and that has been very cleverly exploited in organometallic chemistry for synthesizing transition metal sigma alkyl complexes. Now, just a brief discussion on this. Olefins, when unactivated, are very electron rich and would not be attacked by a nucleophile, whereas they would be attacked by normally be attacked by electrophiles. But the same olefin, when activated by metal as shown over here, can be attacked by a nucleophile, and this is what is called reversal of polarity or the Umpolong nature. Another method is ligand sigma pi rearrangement, and that is shown over here. This is the seventh method of preparing sigma alkyl complexes. Sigma pi type rearrangement. Five Mn bound to an olefin in presence of sodium borohydride gives the following sigma complex. So, here the borohydride donates a hydride and the olefinic moiety gets resided to a ethyl moiety. So, with this we come to the end of various preparative method required for preparing sigma alkyl transition metal complexes. In this lecture in particular, we have talked about 4 different kinds of methods, starting with metallate acylation, then going over to oxidative addition, then nucleophilic addition of activated olefin, and lastly sigma pi rearrangement of eta 2 ligands. These 4 methods discussed in this lecture is however more specialized and more challenging reactions than the somewhat other 4 reactions which were discussed in the previous lecture. So, now having covered all of the preparative method transition metal sigma alkyl complexes, we go to a very new exciting segment in the next lecture, particularly talking about the properties of transition metal sigma alkyl complexes and their stability. I hope you have enjoyed this lecture and look forward to having you in my next lecture, which will be on properties of sigma alkyl transition metal complexes. Thank you.